All right. So, raise your hand if you've had a bug in your code. Of course you have. Put your hand up. You're lying if you don't put your hand up. Of course you have. That's what most of what this whole thing is. Like it or not, debugging is basically programming. If you think programming is sitting down writing lines of code and getting it right, that doesn't happen. No one does that. That's crazy. And don't expect to do it. If someone paid $250,000 a year to write code, is debugging most of their time, I hate to tell you, you shouldn't expect to be any better than that. And I mean that in the nicest way. I mean that that's what programming is. You're going to be bashing your head against that keyboard, going like, this is broken, I hate my life, this is so stupid, why is it? And then eventually you go like, oh my God, I fixed it, I'm so smart, I'm a genius. Who here's had that weird roller coaster feeling? Of course you have, right? Oh, this is so hard, I'm so stupid, why can't I? Oh, it was easy, oh, I can't believe I figured it out, I'm so smart. That over and over and over again, that's going to be your life if you keep doing this. But isn't the rush of getting it working just so exciting? What? And I see people going, I don't know. Of course it is. So, you've seen bugs. So, to start, there are some fairly rigorous ways to go about debugging. And a lot of them, some of the ways to go about debugging are kind of like hedging against having bugs in the first place. Which seems like, well, yeah, duh, but, you know, the way you start writing your code, you write it in such a way, so incrementally, that as soon as you find a bug, you know where the bug got introduced in one of your little, like the past incremental change you made. The first type of bugs that you probably see are your syntax errors, right? I've had syntax errors in class. And if you look at this particular function here, who can see some of the syntax errors? What do we see? Someone tell me one of them.
The bracket is turning them all around.
This parenthesis there, yeah, you're right. What else? There's no colon. Oh, that's another big one too. What else?
There's 2 F's.
Def has 2 F's. Yeah, you're right. What else? Plus multiply, yeah, I don't know what that is. I'm calling Borkin. It's called Borkin, but I wanted to call broken. Oh, man. Anything else funny about this code? Walrus. I guess it's not a problem necessarily, but I don't really know. It's probably not very helpful either way. Either exists and then we just said walrus and the computer goes, okay. Or it doesn't exist and the computer's going to say unknown symbol, whatever, walrus. Yeah?
Never mind, I thought I saw something.
Okay. So there's really not that much of a strategy to going about fixing your syntax errors other than hitting run and Python going like, on line 17, there's an issue. And then you look at line 17 and you go, oh yeah, there it is. Now, every once in a while, sometimes, depending on the line of code, it's possible that it says like the bug is on line 32, but really it's on the line just before that. So be aware of that. If you're like, there's clearly nothing wrong on line 32, but then on line 31 you go, oh, there's the problem. Sometimes that could happen, just FYI. But for the most part, these syntax errors, annoying, they're gonna happen all the time. They happen to me all the time. But you know, you're just patient, you deal with it. Python's usually pretty good at helping you. Yeah. Then there's type errors. Some things like floating point issues can arise. And let's see what happens if I actually try this. Maybe Python 3 won't. Oh, and I did get this working. Okay, those at the back, I'm guessing you can't see that at all. All right, so let's quickly go in here. Settings. See if I can fix this quickly. Editor. Font. Size 25. Is this better or still too small?
A little bigger.
A little bigger would be nice? Okay. Control Shift S, Control Alt. Is that good? Awesome. See, we got 6.02999999, which is a kind of a funny little thing there, right? But we've learned about this before. We've learned that, like, well, floating point numbers are kind of tricky for computers. So sometimes we need to be aware of this. Who here remembers the trick for something like this? Like if I said, print if that equals, if this works, I'm going to be annoyed because Python's being far too helpful. If that equals 6.03, nope. Run false, right? But I mean, it should, shouldn't it? Shouldn't 2.03 plus 4 be 6.03? But it's saying it's not, which is of course quite frustrating. And we know, like we saw why it's not, because it's 6.029999999999, which is not 1, which is obviously not really correct by arithmetic rules. Yeah, the computer's really bad with decimals. So, what's it complaining about here? Whatever. So, who remembers the trick for dealing with this? No one remembers? Not really? How? Because it's not really rounding, that's just the arithmetic. Float 64, maybe that's a solution. But the easiest solution is this. Well, what were you going to say? Out of where? Oh, that's an interesting idea. Let's see what happens if we do this. No, it didn't change. Still broken. What are you going to say? Last try.
The way, I don't think it was the way you taught it, but the way I remember solving this problem and how I remember to use the trunk function.
The what?
It was like TRUNC function and all that, and you like brackets and you return it.
Okay, well, that'd be like truncating, but that would get rid of the decimals.
That's the way I remember solving it that way.
Well, the trick is you take the absolute difference. Here, I'll put that back, and then I'll do print the absolute difference of 2.03 plus 4 minus 6.03. So I want to check if the sum of these things is equivalent to this thing, but I'm worried about my floating point numbers. So I take the difference between the two, and if they are truly equivalent, the difference would be 0, right? But we know that we might have an issue, and it's not going to come up as 0. So I can be like, well, it's not so much if the difference is 0. If the difference is less than or something, then we'll say, okay, they're the same. I keep hitting the shortcut for, there we go. I keep hitting the shortcut for running it on Colab, but this isn't Colab. So there we go. Now it's true. Great. And you might say, yeah, but they're still not the same. Okay, you're not wrong. But I mean, if I'm doing a calculation based on my measurements in chemistry class or something, how accurate was your value really? Like, did you really have a times 10 to the negative 1, 2, 3, 4 precision accuracy? Maybe you did. Okay, so just go, okay, there's no way you're getting anything better than this. It's true, perfect. So there is going to be a threshold where you're going to go, okay, they're the same. Now, if you're doing anything with like pure theoretical and actual numbers, okay, sure, you might have problems, and there are ways to address that. But this is the easy, handy trick for checking the difference, or checking if floating point numbers are the same. Just FYI, remember that. Sometimes type errors are things like, well, you can't add a 2.03 and octopus together. Yeah?
Just do what you did before with the previous question, that you can add too many zeros.
Yeah, you could, because probably in terms of how precise that floating point number could be in general. So let's see. Let's go. Still true for me. Ah, there we go. Well, if we are capable of getting that level of precision, then we should want it to be false, I guess, right? But then again, no, we shouldn't, because it would have been correct if it really should be equivalent. So yeah, I don't know. If you really can get times 10 to the negative 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. Whew, times 10 to the negative 23. You are a magician with your instruments. Anyways. So type error. Now, a funny thing about Python, like the values have types associated with them. You know, every value is like 1, it's an integer. 1.1, well, that's a float. Hello, that's a string. They all have their own type. But an interesting feature of Python is, you know, we can get a little like loose with our types. Like if I've got a variable called something, and I say something equals 1, okay, the variable has the value 1 in it, and the type is an integer. But then I can say something equals hello, and suddenly the value is the string hello. So the variable can flip-flop. In a lot of other programming languages, though, we have much more stronger set of rules for types. If I have an integer, and I want to make a variable for an integer, I make a variable for an integer, and I can only put integers in there. Asterisk. That's weird with primitive types, but let's not worry about that. So this right here, let's do this. I may have done this one already for us, but when I hit run, what will I see? What's it complaining about? Okay. When I hit run, what will we see? It'll concatenate the inputs. Because they're strings. So if I hit run and say, give me a number, 1. Well, 1 plus 1 is 11, of course. Which it is if they're strings. Because plus on strings is concatenation. But if you weren't, like, let's say you wrote this code and you didn't test it properly, and you forgot to convert them to integers, but you wanted them to be integers, and you wrote this giant piece of code and you're hitting run, and you've got this bug in there, you've got a big problem. Suddenly all your 2's are 11? What? That doesn't make sense. In other programming languages, like Python's fine with this. It's fine to let you shoot yourself in the foot. Like, yeah, you totally meant that, right? And a lot of people get really excited because with Python, oh, I don't need to worry about types with variables, it's wonderful. Well, that actually ends up creating a lot of trouble. You might not really actually want what you think you want. Because if this was another programming language, I would say add2 takes an integer a and an integer b. This is not the correct syntax for Python, of course. And then if I tried to run it and I tried to call add2 with 2 strings, it wouldn't even let me start running the code. Where Python will run it and give you the bad result, other programming languages would be like, no, I don't know what add to is if you give me two strings. I can do it if you give me two integers, but I can't do it with strings. Pardon?
How do you make it so that it will not blend if you gave it two strings?
You can do something called type hints. In fact, I'm curious. Will it?
Yeah, I tried to do it and it wasn't working on Colab phone, so did I do something?
You probably did do something wrong, but let's not worry about that right now. All right, so I'm using the word simple error to mean like an error that like when you're running it, maybe it just crashes, doesn't work, right? Who here's seen something like index out of bounds or something and your program crashes, you know, okay, sometimes it's really sometimes it's more obvious than other times about what the error is. And then sometimes you might have an example piece of code like this. This program is in a 1,000 line chunk of code, and I hit run and it's giving me the wrong answer. It's going to be very difficult to find where the problem is. It's going to run, and maybe you don't even know. Maybe it's doing some crazy complex calculation. You hit run and it's giving you an output. But the output's wrong because it assumed that you thought 11 instead of something else. So some bugs, like logic errors, issues like that can be a lot more difficult to decipher, to debug. So logic errors. These can be literally deadly. There are countless examples of really bad logic errors. And you've probably heard of some of these. And we're going to look at a couple of strategies, though, for finding potential logic errors. The first debugging tool in your tool belt is print. Print every value out. If you hit run and you're like, I'm not sure that's right, great, okay, now start tracing through it. Okay, well, that might be a pain. Well, you know what? If you print out the values as the function runs, you can keep track of what the values are, and as soon as they deviate from what you think they should be, what you expect them to be, well, now you can start narrowing down where the code is. If you've got an if statement that you're like, this if statement should be running, but I don't think it is, you can throw a print statement in that if condition, like right after in the block, saying like, did I get here? If you did, oh, okay, so you actually did get into that if statement, so your bug is somewhere else. Maybe you didn't get in there. Okay, great. Maybe print out, right before the if statement, print out the values of the things you're checking. Are they what you expected them to be? Throw prints everywhere. If you're lost, throw prints in there. If you're writing code for a problem that you're not even sure how to solve yet, throw prints in there to see what you get when you run what you currently have. Yeah?
One of my most major codes, I had a print statement on every second line in the entire thing because I'm like, I have no clue what's breaking. Okay, if it gets here, okay, I know it's working. I know it's working. I know it's working. Find out how it's working. It was just printing twice.
Yeah.
That's basically the best way I had it solved.
And that's a fine strategy. Careful though, because my code was always littered with stuff like this, and it upset the TAs. So, I don't know. I don't know how sensitive the TAs are for this class, but just be warned. And my code is also, it's not that it had these in there, it had a bunch of these commented out in there. Because it's like, well, it's working now, so I don't need it, but I don't want to delete it just in case it stops working again, so I'll comment it out. And then you forget about it because you don't see it do anything, and then next thing you know, your code's littered with commented out print statements of your frustration. So, let's do this activity here real quick. Here is count numbers up to n, okay? And there's a description there. This function adds up all the numbers from 0 to n exclusively. Example 5 would be 0, 1, 2, 3, 4. And the number we're counting to, no, we do not count n. Return the sum of the numbers. Great. That's what this function is supposed to do. So, copy this function into Colab or something, hit run, and find the problem. And I'll give you a hint. Throw print statements in there to keep track of what the values are and if they are what you think they should be. Do that. Take a couple minutes to work on this one. Oh, there's an issue here. This should be unindented. If you're feeling fancy, go and report this issue on the GitHub page. Get rid of this. See, I hear you figuring it out. That's the sound of someone debugging. Yeah.
So if we enter 5, or is it supposed to be 1 plus 2 plus 3 plus 4 plus 5?
No, it's supposed to be 1 plus 2 plus 3 plus 4.
Okay.
Yeah. Raise your hand if you figured it out. Raise your hand if you want like just 1 more minute. You'll totally get it. Okay, take the minute. Okay, this is the print this is my print. I'm going to print out a couple of values. I'm going to print out N, C. I'll check this. Like, don't forget, like it's not just about printing out values. You can print out the result of an expression, like is C less than N, which is of course the while loop condition. And I'll print out the current total. All right, let's see what happens. All right. So the result's 15, but we know it should be 4. So clearly 15, there's a problem. So let's look at the results. So I look at the code and I go, okay, the code is just a loop. you know, and it's adding to the total, counter, like every counter we use in while loops, whatever. So what's going on? Well, n is 5, that's correct. C is 1. C is, like, 1 is less than 5, so true, and then the total would be 1. That makes sense. 1 starts at 1. Next time through the loop, well, 5 is still 5. We added 1 to the counter, so the counter's now 2. 2 is less than 5. And then 1 plus 2 is 3. Add 1 to the counter, 5, 3, true. And then the previous sum, which was 3 plus 3 is 6. Okay, great. Then we say, okay, it's 4. 4 is less than 5, it's 10. But now I think I see the problem. The while loop said run, well, counter is less than 5. Yet, my print statement is in this loop. So clearly, the loop actually ran. But 5 is... like 5 is not less than 5. It even told us there. But somehow my loop ran when counter was 5 or something? What's going on there? Maybe it's the position of my print statement. Maybe it's just a coincidence, because remember, counter will become 5 and then not run the loop. But then again, it just ran the loop. So something funny is going on. Clearly, I know the issue is the fact now that counter got to 5 and we entered the while loop, but I don't want to add 5. Maybe the issue is I did less than or equal to 5. Oh, no. That's not it. Okay. You know what? When C is 4, what's the first thing that happens in that loop? It turns into 5. And then what do we do with that C? We add it to the total. There's the problem. Maybe. Let's just see what happens. Okay, it worked. And look at that. Look, we even see it runs when it's 5, but that's because we incremented it to 5. Then it went up to the loop and then didn't run. There we go. Obviously, I was being like very verbose about this process, but this is effectively the process. This is the easiest, quick and dirty strategy for finding your bug. I want to be clear though, when I say it's easy, I mean the strategy of just typing in prints everywhere. That's easy. Using it though to actually find the bug takes a bit of finesse. But that's one of the things that you practice and you learn. This is really great when you have like a function you just wrote and it's not doing what you want and the function's not very big. Maybe throw a couple of prints in there, see if the values are following what you think they should. Any questions about this strategy? Raise your hand if you've used this before, where you just throw prints in there and you're like, well, is that what it's doing? Good. If you haven't, start doing it. It's great. So the strategy goes kind of like this. If you break it down, is you go, okay, I know what I want my function to do. And then you look at the values. And I know what the value should be as it runs, if it was correct. And then you compare it to what you actually see the values are. Then you look for those differences. Where you find the differences, hopefully you can find the problem. But this isn't a silver bullet. There's no silver bullet strategy for debugging. And debugging really is kind of a bit of an art. You just kind of get a sense of it. So before when I said like, oh, you shouldn't expect to not have bugs in your code, just like the software engineer making big bucks, I suppose the difference between you and them at this stage is they're going to have bugs. Maybe some of the bugs will be different, but they have experience on finding and debugging. You are still learning that process. And it takes time. The number of times I always hear people, not so much at this stage of the course, and none of you have ever said this, of course, is you come in to office hours and you're like, I've been working, like my code isn't working and I'm going to give up. And say, well, how long have you been looking at it? Well, I wrote it and it's not working. Like I'm upset. Yeah, but how long did you try to fix it? How long did you spend to try to fix it? Like, what do you mean? Like, well, when I write my code, it's not correct. Yeah, no one does that. No one sits down and writes perfect code, ever. Ever. It doesn't happen. And if it does, it is a freak accident when it happens. Another strategy, and this strategy can go with the printing out the value strategy, is, before I said up here, the strategy is come up with an idea of what you expect the values to be. Like, I know what the function is supposed to do. I know how I wrote the function, and if the function was correct, this is how the value should change. That's great if you've got like a little function. But as soon as it gets bigger and you've got a number of values to keep track of, good luck keeping track of that in your head. That's not going to happen. So grab a sheet of paper, your pencil, and scratch down what the value should be, then try the print strategy. See how it compares. Pencil on a paper is the programmer's best friend. A lot of new programmers think it's silly. My office is, I could take you all to my office and empty my recycling bin, and it's going to be full of pages of just chicken scratch, code things, logic, and how things are flowing. That's what it is. That is going to be a lot of what you do. One of the best investments I ever made was in second year university. I bought myself a little whiteboard. Oh, it was glorious. I loved it because all of my ideas I can put down there. I didn't waste the paper, and I can draw nice and big. I'm really sloppy at writing, so when it's big, the sloppiness just kind of looks cartoony. So I didn't feel as bad. Whiteboard is fantastic. If you don't have that, pencil and paper is great. Whiteboards, though, especially when I got to like third year and fourth year, like the place where all the undergrad computer science students hung out was one of the computer labs that had this giant whiteboard in it. It was huge. And we hung out there not because we wanted to use the computers. The computers were crap. We hung out there because that's where we could access the whiteboard, and that's where we just solved all our problems. It's really handy. If we didn't have access to a whiteboard, we'd be stuck with pencil paper, which is okay, I guess. But, yeah. So, pencil paper is fantastic. Rubber duck debugging. Have you heard of this one? It's a real thing, despite what you think. See, there's a Wikipedia page and everything. How often, what's this? Oh yeah, right. I made an app that you can talk to. It's a rubber duck. How many times have you been like, my code's broken and I don't know what's going on? And maybe the person next to you in lab is like, well, what's it doing? And then you're like, okay, well, look, here's what's supposed to happen. So it starts going like this, and as you can see here, it's adding those values together, and then on the next line of code, it's going to, oh. How many times has that happened to you? There you go. Yes, exactly. It happens all the time. Articulating the logic, the thought process out loud works so well. So well that it's become a joke that programmers have little rubber ducks on their desk that they talk to. Honestly, the amount of value I get out of having, like when I was doing my PhD, and maybe I was writing code and it was stuck, and I asked my buddy to come over to help me have a look. I knew that when I was asking my buddy, who was in the office next door, to come over and have a look with me, and I'd explain the code to him, I knew there's no way he's going to find the error. But at least I could talk to him. And then I just start talking out loud at another human, not a rubber duck, I guess. But then I found the problem by just talking out loud. The rubber duck strategy, if you don't have a rubber duck, grab a teddy bear. Grab whatever. Grab your roommate. Talk at them, and you might be surprised. Yeah?
It's essentially just forcing yourself to talk to someone
It's because when you look at it, and you're looking at your code and you're thinking mentally, chances are you start to make those skips. You start to make those assumptions. But when you start talking out loud, you have to really hit every line of code, every function call, everything. That's a big part of what helps it, is that you're forced to not make those jumps. In lab, when I come around, and I'm like, okay, well, what does this function do? A lot of people try to impress me and be like, oh, it's adding up all the even numbers. No. What's happening on that line of code? Oh, well, it's going to do. No. What does that line of code do? I'm not trying to be an ass. I'm trying to show you that level of stupidity, that level of granularity of what's happening there, that's how you have to think. That's the magic there. If you try to be smart, if you try to jump all those steps in there, you're not going to find it. You're going to be in big trouble. You have to dumb it down. So if I ever come up to you in lab, or maybe you come into office hours and you're stuck, I'm like, okay, what happens on that line of code? I'm not trying to be an ass to you. Like, tell me what happens there. And you're like, I know. No. Chances are maybe you don't know, and that's actually the problem. That's the strategy we all take. Here's another one, delta debugging. This one might feel silly, but it's not a bad strategy at all. You wrote your function, it doesn't work. Your function's 7 lines of code. Okay, great. You know what? Comment all the lines of code out. Hit run. Well, it won't work because Python will say, you've got a function, but there's nothing in it. Okay, fine. Uncomment one of the commented lines of code back in. Hit run. Does it do what you expect? Okay. Add another line of code back in. Does it do what you expect? Add another line of code back in. Does it do what you expect? Just do this slowly. This is kind of a way, though, at getting to really the core important strategy here is it's not even really a debugging strategy. It is how to hedge against having to debug in the first place. The number of times I see in lab people sitting down, writing the whole function, hitting run and going like, it's not working. It's because you're going about it all wrong. You start by writing 2 lines of code. Hit run. Does it do what it should be doing? Okay, add that loop and print out the values. Is it doing what it should be doing? Okay, great. Now add the next thing in. Is it doing what it should be doing? If not, you know where the problem is. You introduce the problem with that last one little addition. Great. Now it's a hell of a lot easier to debug than writing the whole function and going like, well, it's not working. Take your time. Build it and test it. Build it, test it, build it, test it. Next thing you know, you've debugged while building it. That strategy there is a really good way to like just do the debugging kind of like baked into the programming. Don't sit down and try to write the whole function. Start piece by piece. If I'm telling you, write a function to sum up all the even numbers between 0 and n, think to yourself, like, don't think like, oh, how am I going to do that in a whole function? No, think, okay, I need a function. I'm going to need a loop. So I've got a choice to make. Do I want a while loop, a for loop, or, if it's a while loop, I'm going to need a counter. So you know what, let's go there. Let's create the function, create the counter, use a while loop, and make sure it's doing what it should be. Okay, good, great. Now, when should the loop end? Well, at n. So, okay, I'll make sure it's doing that. It does end at n. I can do that by printing out, like, is the counter less than n? Great, easy. Keep doing that, and next thing you know, you're done. Chances are you've already been breaking down all of these problems in your head like that. It's just you didn't test them along the way. You didn't make sure that they work. Now, here's another thing, too, that goes with debugging, is testing. Just because someone said, write a function to do x, y, z. Write a function to add 1 to what you give it. And then you call the function, and you put in 6, and you see a 7. Or, how about this? Write a function to square the value. Okay? You wrote it, you put in 1, you get a 1 out. That's correct. Great. But can you conclude that your function's correct? Of course you can't. You tested one value, and one value is right. Does that mean it's right all the time? No. It just so happens that what if it just so happens that the function that is supposed to be squaring the input, all it did was return the input. It didn't actually do anything. So if I put in 1 and I get 1 back, it's correct. If I put in 2 and I get 2 back, I should be getting 4 back. You got to make sure you're being thorough with your tests. Don't just test 1 or 2 values. Test a bunch and then try to break it. When you write code, you got to try to break it. And then you think of what we would call like the edge cases. These are like, okay, I want to sum up all the values between 0 and n. What happens if I make like n 0? How does it act? Right? That would be like an edge case. And that would be a good one to test. What happens, you know what I mean, right? That's why it's an edge case, because if I say sum up all the numbers between 0 and n, and I say, well, n is 0, that's kind of a peculiar one. Because if I ask you, sum up all the numbers between 0 and n, where n is 0, you're going to go, 0? Which is correct. But does your function deal with that? Because that's kind of a funny little scenario, right? Does it do that, or does it do something funny? Because you could write that code where you start with 1. You kind of ignore 0, right? Because you're like, well, 0 plus anything, like, it's going to be 0 plus 1. So whatever, let's start at 1. Forget 0. But if n was 0 and you start returning 1, you're wrong. Let me show you real quick here. So I think I'm super smart. So some numbers, okay? If I'm like, you know what, I'm smart, I can save a step, because 0 plus 1 plus 2 plus 3 and so on is the same as 1 plus 2 plus 3 and so on, right? Adding the 0 doesn't do anything. So let's forget that step. Let's just start it at 1. So C, our total equals 1, and then C equals 0, while C is less than n. No, I guess we could do, we'll have to start the counter at 1. Well, C is less than n. Total plus equals C. C plus equals 1. Return total. So print some numbers, and we'll give it 5. Uh, 11. That doesn't seem right at all anyways.
You're adding 1 to it as it's always
Starting
starting at 1.
at 1.
And then you're adding 1 to it, so you're adding 1 twice.
I'm adding 1 twice. You're right. Thank you. 10. Perfect. That's correct. 1 plus 2 plus 3 plus 4 will exclude 5, like the previous one with the bug. Great. So this seems quite correct, right? But what happens if I say 0? 1. So it's your function is going to be right 999,999 times out of a million. But that one time, in that funny edge case, it breaks. This is wrong. So the function seems right. It's right most of the time, but it's wrong. You got to be careful. You got to think of these edge cases. Any questions about that? Okay, see you later.